We need to talk about the confidence game.
Uh-huh.
We've all seen it. You ask an AI a question, maybe something a little complex for work, or a logic puzzle.
Right.
And it gives you this beautifully written, structured answer. The grammar is impeccable, the tone is authoritative, and it just feels right.
It does.
But then you look closer, maybe check the math, and you realize it is completely wildly wrong.
It's the smooth talker problem. The model is, optimized to sound convincing, not necessarily to be factually accurate.
Right, it's like that guy at the party who knows absolutely nothing about quantum mechanics, but uses all the right buzzwords so confidently that everyone just nods along.
Yeah.
In the industry, we call this hallucination, but I feel like that word is too soft. It's more like confident fabrication.
I agree.
And for anyone trying to use these tools for engineering or finance or actual science, that gap between sounding smart and being right is a deal breaker.
It's the single biggest hurdle to adoption. I mean, if you can't trust the output, you can't automate the process.
So today, we are diving into a paper from Google DeepMind that suggests we've been going about fixing this all wrong. They've proposed a method that might finally force AI to check its own homework and actually mean it.
It is a significant shift. The paper is titled Generative Verifiers, Reward Modeling as Next Token Prediction.
Which is a mouthful. But stick with us, because what they are proposing is basically, well, it's like lobotomizing the old way of checking AI and replacing it with something that looks a lot more like human reasoning.
That's a good way to put it.
But before we get to the solution, we have to understand the band-aid the industry is using right now. It's called best of N. Can you break that down?
Sure. The logic is actually pretty similar to how humans solve hard problems.
Okay.
If I give you a really difficult math question, you probably won't get it right on the very first try. You might, brainstorm a few different approaches.
Right.
Best of N does exactly that. You ask the AI to generate, say, 16 different solutions to the same prompt.
Okay, so I have a stack of 16 potential answers. Some are probably gibberish, some might be close, and hopefully one is perfect.
Then you bring in a second mechanism, a verifier or a reward model. Its only job is to look at that stack of 16 answers, rank them, and hand you the winner.
That sounds logical. You generate a bunch, you pick the best one, so where does it fall apart?
The problem is the judge, the mechanism picking the winner. Currently, most verifiers are what we call discriminative reward models.
Discriminative, that implies it's just making a sort of binary choice.
In a way, think of it like a teacher who doesn't actually read your essay, but just scans the shape of the paragraphs and slaps a grade on the top.
So it looks at an AI's answer, which could be pages long, and it just outputs a single number.
A single numerical score, just a scalar number, usually between 0 and 1.
So it looks at a complex explanation of, say, the causes of the French Revolution and just says 0.8.
That's it. And think about the signal loss there. When a model outputs a probability score of 0.8, it isn't telling you what is right or wrong. Is the date wrong? Is the logic flawed?
Is the tone just off? You have no idea.
A scalar score compresses all that nuance into a single digit.
It's a black box. You're asking a system to judge complexity, but you've taken away its ability to speak.
You are lobotomizing its reasoning center. You're taking a large language model, which is designed to process tokens, language, and meaning, and forcing it to act like a pocket calculator. It's a waste of the model's brain.
It's like hiring Shakespeare to grade papers, but telling him he isn't allowed to write comments in the margins.
Yeah.
He can only use a rubber stamp that says pass or fail.
And that is precisely where this new paper from DeepMind pivots. They asked a very simple question. What if we let Shakespeare write the comments?
What if verification wasn't a math problem, but a language problem?
Exactly.
This brings us to the generative verifier concept, or GenRM.
Right. The big shift here is moving from discriminative to generative. So instead of outputting a silent score, the model is trained to predict the next token. Specifically, it is trained to answer the question, is the answer correct, with the generated word yes or no.
Hold on, I want to push on that. How is generating the word yes or no fundamentally different from giving a score of 1 or 0? Are we just swapping a number for a word? It feels like semantics.
It feels like semantics, I get that, but mechanically, it's a world of difference.
How so?
When a model predicts a token, a word, it is using its entire pre-trained understanding of language. It's accessing the same neural pathways it uses to write poetry or code. It's what DeepMind calls unified training.
Unified training. So we stop treating the writer and the grader as different species.
We merge them. DeepMind found they can train the model to generate solutions and verify solutions using the exact same loss function standard next token prediction.
So the same brain that writes the math proofs is the brain that grades it.
And this creates a symbiotic relationship. It turns out, learning to grade makes the model a better writer, and learning to write makes it a better grader.
That makes sense.
Because the weights are shared, any improvement in logic on one side it bleeds over to the other.
By learning to spot mistakes, you inevitably learn how to avoid them. But they didn't stop at just yes or no.
No!
Because yes or no is still just a grade. They added the special sauce, chain of thought.
GenRM QT. This is where the magic really happens.
Instead of just asking, is this right? They prompt the verifier with something like, let's verify step by step.
And that simple phrase forces the model to write out a critique, a paragraph explaining its logic before it decides if the answer is right or wrong.
So it has to show its work.
It has to externalize its reasoning. And to show you why this matters so much, we have to talk about the cable bundle problem from the paper.
Oh, yeah.
Because this example perfectly illustrates that confident hallucination we talked about at the start.
I loved this example because it's so mundane. It's not quantum physics. It's a guy named Tim trying to save money on streaming.
It's a classic word problem trap.
So here's the setup. Tim wants to save money. He currently pays $60 for cable. He's looking at switching to streaming.
Yeah.
He sees that Netflix is $10. Then there's a bundle of Hulu and Disney Plus Play.
Mm-hmm.
Normally, those are $10 each, but if you bundle them, you save 20%. The question is, how much does Tim save by canceling his cable and switching to these services?
Sounds like simple algebra. Most of us could do this on a napkin.
You'd think. So the standard AI generates a solution. And listen to this logic. Okay, Hulu and Disney Plus are $10 each. The bundle costs $10 times 80%, so that's $8.
Okay.
Total cost is $10 for Netflix plus $8 for the bundle, which is $18. Savings is $60 minus $18 equals $42. Boom. Done.
It sounds perfect, doesn't it? The grammar is right, the arithmetic steps look clean. If you just glanced at it, you'd verify it.
I almost did when I was reading the paper. I was like, yeah, 20% off 10 is 8. Logic holds.
But you missed the premise.
Right. It calculated 80% of $10, but the bundle includes 2 services. It should have calculated 80% of $20.
So the bundle price should be $16, not $8. The math is valid, but the logic is flawed.
Exactly. Now, here's the kicker. They fed this wrong answer to the standard discriminative verifier, the one that just gives a score. What does it say?
Oh, I remember this.
It gave it a score of 0.999.
Total certainty.
It looked at that wrong math and said, this is absolutely perfect.
Because the tone was confident. The standard verifier got fooled by the style. It saw the structure of a math proof and assumed the content was correct.
It couldn't read the logic. It could only score the vibe.
Yes. But then they ran it through the GenRM QT, the one that thinks step by step.
And what happened?
Because it had to write out the steps, it couldn't skip the logic. It wrote, Step 3. The bundle of Hulu and Disney Plus costs $10 times 80% equals $8. And then it stopped. It flagged it.
You caught it.
It wrote, incorrect. The bundle costs $10 plus $10 equals $20. With the discount, it should be $16.
And consequently, it marked the final answer no.
That is the difference between checking a box and actually reading the work. By forcing the model to generate the critique, you force it to process the logic sequentially.
So we have the theory, and we have this anecdote about Tim and his cable bill. But what about the hard data? Did this actually move the needle on the benchmarks?
The results were startling. They tested this on GSM 8K, which is the standard grade school math benchmark.
Which, to be fair, is usually pretty tough for smaller models.
It is. Now, using the old LLM-as-a-Judge method, they were getting about 73% of problems solved.
Okay, 73%.
With GenRM code, this generative verifier, that shot up to 93.4%.
That is a 20-point jump. That's not an incremental improvement. That's a generation leap.
And context is vital here. This was achieved using a Gemma 29B model.
Smaller model.
Right, a relatively small open weight model. But with this verification method, it was outperforming massive proprietary models like GPT-4 and Gemini 1.5 Pro on this specific metric.
That's wild. A smaller, smarter verifier beating the giants just because it takes the time to think.
And it wasn't just math. They tested it on algorithmic tasks like word sorting and letter concatenation.
Yeah.
Performance there jumped from 5% to 45.3%.
Going from 5% to 45% is basically the difference between useless and functional.
Absolutely.
But I want to pause here because there's a catch. We're talking about generating critiques, running checks.
Yeah.
This sounds computationally heavy.
You've hit on the main trade-off.
This touches on inference compute. Because the verifier is generative, you aren't just running it once, are you? To get these results, they used majority voting. Can you explain how that works?
It's exactly what it sounds like, democracy for algorithms. Instead of asking for one critique, you might ask the model to generate 32 different critiques for the same answer.
32.
Or 64. You let the model examine the answer from multiple angles. Maybe one critique misses the error, but if 20 out of 32 critiques say, hey, the map on the bundle is wrong, then the system marks it wrong.
But let's look at the price tag. Generating 32 critiques for every single answer.
Yeah.
That's 32 times the compute. Isn't that prohibitively expensive?
It is expensive. There is no denying that. We are trading compute for reliability.
Right.
Right now, that's costly. But the paper suggests something very important for the future of AI economics.
Which is?
It suggests that scaling inference compute, so giving the model more time to think after you ask the question, is actually more efficient than just making the model bigger and bigger.
So it's better to have a small model that thinks for 10 seconds than a giant model that answers instantly.
Precisely. We are moving from System 1, thinking fast, intuitive, prone to error, to System 2, thinking slow, deliberate, and logical. It costs more energy, but it gets the right answer.
Which brings up something that I found really surprising in the report regarding what these models learned. They trained these verifiers on the easy stuff, on grade school math, but then they threw them into the deep end.
The easy to hard generalization. This is scientifically perhaps the most exciting finding in the whole paper.
So they trained on GSM-8K, which is questions like if Tim has 5 apples.
And then tested them on Math 500, which is high school competition level, and MMLU, which includes abstract algebra and college math.
Stuff I definitely cannot do.
Stuff most people can't do. And the verifiers worked.
They did.
On the math data set, performance improved from 28% to 44.6%. On abstract algebra, it went from 37.9% to 53.5%.
Wait, how is that possible? If I only learned 5th grade math, I can't grade a college calculus exam. I wouldn't know if the answer is right. I'd be lost.
That's the human assumption. We assume knowledge is subject-specific. But what this suggests is that the model didn't just memorize the answers to grade school problems.
It learned something else.
It learned the process of verification. It learned logic checking.
It learned the structure of an argument.
Think of it like the Karate Kid effect. Mr. Miyagi teaches Daniel to wax the car and paint the fence.
Wax on, wax off.
Right, simple, repetitive movements. But then, in the fight, Daniel realizes those movements are actually blocks and strikes. By training on simple word problems, the model internalized the structure of verification.
So it learned that step B must logically follow step A.
Exactly, and that structural rule applies whether you are doing second-grade subtraction or multivariable calculus. It's checking the validity of the flow, not just the arithmetic.
That is huge.
Yeah.
It means we don't necessarily need a PhD-level mathematician to train an AI to do PhD-level math.
We just need to teach it how to check its steps on simpler problems.
Wow.
Which is fortunate because getting PhD-level data is incredibly hard. And that leads us to the final piece of the puzzle. The data bottleneck.
Right.
Usually to train these things, you need expensive human data. You need humans writing out those critiques. And humans are slow, expensive, and they get tired.
So what did they do?
So DeepMind didn't use humans. They used synthetic verification rationales.
Robot teachers.
Essentially, they used a model Gemini 1.0 proto act as a teacher and generate the step-by-step critiques to train the smaller models.
Hold on, though. I have to play devil's advocate here. We're talking about AI grading AI. Using data written by AI. Isn't this just model collapse waiting to happen?
It's a huge risk.
If the teacher model hallucinates, doesn't the student just learn to hallucinate more confidently?
Yeah.
It feels like the blind leading the blind.
That is the primary risk with synthetic data, for sure. If the input is garbage, the output is garbage. But they used a clever safety net called reference-guided grading.
How does that work?
When the teacher model was generating the critique, they gave it the correct answer sheet.
Ah, okay. So the student AI makes a guess. The teacher AI sees the guess, but also holds the answer key in its other hand.
Correct. So the teacher model isn't guessing. It looks at the student's work and says, ah, I see where you went wrong compared to the answer key. And then it writes a perfect critique.
And the student model trains on that critique.
Exactly. So you anchor the synthetic data in ground truth. You aren't just letting the AI drift, you're tethering it to the right answers.
Then did it work?
It did, and the quantity mattered. They found that simply scaling up the amount of synthetic critiques prevented the model from overfitting. It smoothed out the noise.
So let's bring this all back together. We started with best of n. which was just generating a bunch of answers and hoping a black box could pick the winner.
And we are moving toward a world of transparent linguistic reasoning. We aren't just looking for a score. We are asking the AI to explain why something is right or wrong.
By treating reward modeling as a next token prediction task, by making it just another language game, we unlock chain of thought, we unlock majority voting, and we get models that are dramatically better at math and logic.
And for the listener, the application here is reliability. The next generation of AI tools won't just be creative engines, they will be engines that can show their work.
They'll be able to self-correct before they ever show you the answer.
No more confidently wrong answers about cable bundles, or financial projections, or code.
It really feels like we're crossing a threshold from mimicry to reasoning.
I think that's fair. And it leaves us with a very provocative thought. The researchers found that generating critiques is sufficient to catch errors, even if the critique writer isn't smarter than the solution generator.
Right, the verifier just needs to follow the logic like we saw with the calculus example.
So if AI can effectively grade its own homework using synthetic data, how far are we from a self-improving loop?
If human supervision is no longer the bottleneck for reasoning tasks, and AI can generate the data it needs to get smarter,
then the ceiling for AI capability might be a lot higher and a lot closer than we think. If the machine can define its own curriculum and grade its own tests, the loop tightens fast.
a dizzying possibility to end on. Well, I'm going to go verify my own thoughts step by step. Thanks for diving in with us.
Pleasure as always.